In this video, we'll introduce the essential skills you need to use a high-performance computing cluster. But before we dive into the practical aspects, let's take a moment to explain what a HPC cluster actually is. A prominent example of a HPC cluster is Frontier, developed by the Oak Ridge National Laboratory in the US. In 2022, it became the world's first exascale supercomputer, meaning it's capable of performing over 1 quintillion calculations per second. Although Frontier is a state-of-the-art cluster, its underlying architecture is similar to that of most HPC clusters. So what exactly makes up a typical HPC cluster? Let's take a look. At their core, these clusters consist of hundreds, if not thousands, of individual computers, known as nodes. Each of these nodes has its own CPU and memory that can operate independently. However, they are all networked together so that they can collaborate on solving larger, more complex tasks. Let's take an example of a Tier 2 HPC cluster, SLURM. This machine is located in the University of Warwick in the UK and supports cutting-edge research for several universities. SLURM offers a range of node configurations tailored to solve different types of tasks, but today we'll focus on the standard compute nodes. Each of these compute nodes contains not one, but 2 AMD EPYC processors. These server-grade CPUs are optimized for parallel workloads and feature 64 cores and 128 threads each, far surpassing the core count of typical consumer CPUs. However, as these CPUs contain many cores, they are often clocked at a much lower speed than typical consumer desktop chips, usually in the range between 2 and 3 GHz. They also include a larger cache, which, as discussed earlier in the series, is essential for achieving high performance. In addition, these CPUs also support vector instruction sets, like AVX2, which significantly boost the performance of scientific workloads that rely on linear algebra operations. Since these CPUs are capable of running many tasks in parallel, each node also includes a large memory pool, typically around half a terabyte, to ensure that there's enough memory for all tasks to run simultaneously. Overall, SLURM has around 167 of these standard compute nodes, totaling over 20,000 cores. And this is just the standard configuration. SLURM also offers more specialized nodes equipped with GPUs or higher memory capacities. One of the biggest advantages of using a HPC cluster is that multiple nodes can be used to work together to complete a specific task. In order for these nodes to work together, they must be connected through a high-speed network, typically with a bandwidth of around 100 gigabits per second, which is roughly 100 times faster than you would find in a typical home wired network. This high-speed interconnect helps reduce communication bottlenecks that often affect parallel algorithms. But compute and networking is only part of what you need to solve your problems. But now, what about storage? Most HPC clusters use a centralized network storage system. This storage is hosted on dedicated machines, which provide a shared file system, which is accessible by all nodes in the cluster. These storage nodes can contain hundreds, if not thousands, of drives to make up the total capacity. For instance, SLURM provides 2,600 terabytes or 2.6 petabytes of hard disk storage and 800 terabytes of faster solid-state storage. A centralized storage system is vital for running parallel algorithms, as it ensures that all nodes can access the same software and data while also providing a shared location to store results. So how do users access the cluster? This is done via a login node. These login nodes typically have a similar configuration to the compute nodes, but they are not meant to be used for running computations. Instead, login nodes serve as a gateway for users to connect to and use the cluster, typically over the internet. For security reasons, access is often restricted to users that are connected through their institution's VPN. To connect, users typically use a program called SSH, which creates an encrypted tunnel to give secure terminal access to a login node from a remote machine. A similar tool called SCP, or Secure Copy Protocol, can be used to transfer files from your local machine to the cluster's shared file system. These files should go into your user's home directory, and you can manage these files through the terminal, or use version control tools like Git to upload or download your code. Once all your files are in place, you can also handle other tasks like managing software or compiling your code. Although login nodes can technically run code, doing so is strictly prohibited on most HPC systems. Their role is solely to provide access and facilitate file management, not to perform computations. Running heavy compute jobs on login nodes can disrupt other users, and most clusters enforce strict policies that may result in bans for such misuse. So remember, do not run any computations on the login nodes. Instead, you should submit a job to the cluster's scheduler. A job specifies the compute resources required, such as the number of CPUs or nodes, and how to run your code in a self-contained way, usually wrapped up in a bash script. This job is then passed to your cluster's centralized scheduler. The scheduler then attempts to allocate the requested resources and, once available, signals the appropriate nodes to begin running your job. A widely used scheduler is SLURM, which is a simple Linux utility for resource management, which we'll explore in much greater detail later on in this video. Using a scheduler allows for multiple users to share the cluster efficiently, avoiding interference between jobs. Additionally, if no resources are available, your job is placed in a queue and will start automatically when the requested resources free up. Now that we've covered the basic structure of a cluster and how users interact with it, let's move on to the practical side. In the next section of the video, we'll walk through how you can connect to a HPC, transfer files, and submit jobs using the scheduler. Let's get started. As an example, I'll be using the University of Nottingham's on-premise HPC service called Ada. In general, all of the skills that we learn in this video should be transferable to your own institution's HPC, but there might be a few differences on how you access the system, depending on how your institution has set up their HPC. If you haven't connected to one of these systems before, you might have to apply for access first, and for that, I'd recommend contacting your IT services. Once you've gained access, you should read through the Getting Started documentation that should be provided by your institution, as these will give you tips on how you can connect to your specific cluster and include any extra information that you might need about using the system. In the case of Nottingham's HPC, one of the things you have to do is use a VPN, which is a virtual private network. This VPN gives me access to internal University of Nottingham systems that aren't accessible to the wider internet. One of these services is the Ada HPC. Setting up access to the VPN is beyond the scope of this video, but I'd suggest talking to your local IT team if you're having trouble. So with that out of the way, let's connect to one of these systems. The first thing you want to do is open up a terminal on your system. For the example of this video, I'm going to use a Linux terminal, but all of the commands that I use for connections should be available on Windows and macOS as well. If you're on Windows, you might have to enable the Open SSH client that comes bundled with Windows, but is not always enabled. I've left a link in the description to this article which explains how to do it. You can check that you have access to SSH by just typing it into the terminal and pressing enter, and you should see an output that looks like this. Now, SSH is a very useful program that gives you encrypted access to a terminal that's hosted on a remote machine. And this is the program we'll use to connect to Ada. The way that you use this command is by typing SSH followed by a space, and then typing your username that you need to access your local system. In this case, this is my university username. This is then followed by an @ symbol, and then you want to put in the address of the computer that you're trying to connect to. In this case, I want to connect to one of the login nodes of Ada, and the address for a given login node is provided in the documentation for the HPC. In this case, the address given looks like a website, which is hpclogin01.ada.nottingham.ac.uk. Now this link is only accessible once you connect it to the VPN. If you're connecting to a different system, the parts that you have to change is your username and the address of the host that you're connecting to. This could also be an IP address, but usually it's provided in the form of a host name. When you have the full command, you can press enter and SSH will attempt to connect to the host. If you're connecting to a host for the first time, you'll be greeted with this message. This message simply asks you to add a fingerprint for the host so that you can securely connect to this host in the future without worrying about a man-in-the-middle attack. And in this case, we do trust this connection, and so we'll type in yes and press enter. If we try and connect to the HPC login node again at this address, our computer will check its fingerprint against the one sent on the new connection to make sure it's authentic. If it's not authentic, it will warn you about this connection. Once we've added this connection, we will be requested to put in a password, and this is usually the password for your IT account. Don't worry if you start typing and you don't see the cursor moving, this is just a security feature, but your keyboard presses are being recorded. Once you finish typing in your password, just press enter. Don't wait too long to put in your password or else your request will be denied. Once you successfully connect, you'll see some login information, and you'll be dropped into a terminal that exists right on the HPC login node. And this is just a bash terminal. If you're not very familiar with using the terminal, don't worry, we don't need to be overly familiar with it to be able to use the HPC, but learning to use the bash terminal is a very useful skill and will come in handy when trying to use one of these systems. But you don't need to have any prerequisite knowledge to follow along with this video. We're in the terminal, but I want to clear the screen, so I'm going to type Ctrl-L, and this will just clear the output from the previous section of the screen. Before I had some Python activated, which is why you're seeing the base on the front, but I'll just deactivate that for the purposes of this video. So once you're logged in, you should see this screen, and one thing to note is that you're now connected to a terminal inside the HPC. And this is as if the HPC login node was right in front of you, and you had terminal access to the machine. We can prove this by typing in the command hostname, which prints out the address of the node that we're connected to. If I type in the same command on a new terminal on my local machine, you'll see I get a different address, which is the name of my computer. So right now I'll just show you a few bash commands that you can use to navigate this terminal environment. The first command that you will want to use is the command ls. And this command will list all of the files and folders in your current directory. And the directory that you start in is your home directory, which is where you want to put all of your files on this system. In this case, the symbol tilde is just a shorthand for your home directory. You can type out the pwd command, which stands for present working directory, to list the complete path to the current folder. In this case, this is in the folder gpfs01, which is the shared folder that's accessible by all nodes in the cluster. Within this folder, we have the home directory, which is where all of the user's home folders are stored, and finally our user ID, which is our own personal folder, in which we have read and write access. Sometimes when we use ls, we want to see some hidden folders as well. So if you type ls-a, you'll be greeted with a much larger list, including files and folders that start with a dot, which are hidden directories and hidden files. So let's say we wanted to change directory, we could use the command cd followed by a path of a folder that we wanted to go into. So let's say we wanted to enter this HPC example folder, we could just start typing the name and then use tab to complete the rest of the name. If you wanted to check what was inside this folder fully, then you could press tab twice and it will print out all of the files and folders that are inside this directory. In this example, there are no folders, and so we'll just press enter to enter this directory. You'll notice that the name of the directory changes here, and if we type in pwd, we'll have changed directory completely. So now we're inside this folder, we can ls again to see where we are, and we can have a look at some files. But since this is a terminal, we can't just open these files like you normally would in your own code editors. If we want to have a look at the contents of one of these files, we have a few options within the terminal. One option is to use the command cat followed by a file name, and what this will do is take the contents of this written file and just print it into the terminal. So you can see this file is quite short, it's just 2 lines of Python. We could even use the Python command to run this file. But let's say we wanted to make any edits. How can we do this through the terminal? Well, one option is to use the command line program nano, which you can kind of think of as a command line version of the Notepad program. If you type in nano followed by your script, you'll be dropped into a new editor in which you can navigate around and add in some statements. Once you're finished, you can exit out of the program by pressing Ctrl X. You'll see whether it's asking whether we want to save the changes or discard them. In this case, I will save the changes, so I'll just press Y. And then we're also asked to specify the name. In this case, I just want to keep the name the same, so I'll just press enter. And now if we do cat main.py, you'll see our changes have been added. And we can run the script again just to confirm the changes have been made. Just very quickly, I want to show you a different command line program that might be available on your systems in case you don't have access to Nano, and that is the Vim editor. Now, there is definitely not enough time to teach you Vim in this video, but I'll just show you the most important thing. So the way that you open this text editor is the same as using Nano, by just specifying the file that you want to edit. And Vim by default has an edit mode and a navigation mode. So at the moment, all we can do is move our cursor around. But if we want to actually make any changes, we have to press the I key on our keyboard. You'll notice on the bottom left hand side, it now says insert, and this means we've changed the mode that we're in. And now we can just edit like normal, or we can just delete the changes that we made before. But the most important thing you have to know about Vim is how to exit this program. And the way that you do this, if you're in insert mode, is to press escape. This will drop you into the normal mode again, where you can navigate around. So what you want to do is type :Q followed by an exclamation mark, and this will force quit out of the program and you're entered back into your terminal. You'll notice that this didn't save any of the changes. If you want to save your changes, you should use :QW, which writes to the file and then quits. Obviously, editing your files here isn't the best experience because you're probably used to using a code editor. And so in a second, I'll show you a more ergonomic way you can work with your files using VS Code instead of using the terminal directly. But for now, I'll just show you one more command that you can use to get back to your home directory. So in this case, we want to get to the home directory, which is 1 folder up from where we currently are. We can use cd again and specify 2 dots, which is a shorthand for the parent directory relative to where I am currently. And you'll see this drops us back in the home folder. Before we switch over to using VS Code instead of the terminal directly, let's try and set up a passwordless login so that we can access the HPC without having to type in our password every time we want to connect. The way you can do this is with SSH keys. So for now, what I'll do is just exit out of this terminal by typing the exit command. And this closes our connection and drops us back into a terminal on our local machine. Now if we want to access the HPC, what we want to do is create an SSH key, which will let us connect to the HPC without using a password. One way you can check if you've already created one of these keys is by typing ls tilde, which is your home directory, /.ssh. A quick note, if you're on Windows, you can type dir tilde /.ssh. And you'll notice on my Windows system, I do have these files, id_rsa and id_rsa.pub. If you have these two files on your machine, you can skip the next step because you already have created SSH keys. But if you don't have those files, I'll show you how to create them now. Creating these files is as simple as using a command line tool called SSH keygen. So you just type in this command, press enter, and you'll be greeted with a few options. By default, this will save your key in id_rsa. And this is the default location which you want to use, so just press enter. You'll also be asked to enter a passphrase for this key, and this is often recommended for security reasons, to make sure that if anyone gets access to your private key, they can't just log into any machines for which you've allowed passwordless logins. But for this example, I'm not going to add in a passphrase because I want to use it as a completely passwordless login. You're asked for the same passphrase again, so I'm just going to press enter. So now it will have created some random key, but we need to do one more step to make sure that the HPC login node accepts this key for a passwordless login. There are a few ways we can do this, but the easiest way is to use the SSH copy ID command. And this works just like the SSH command if we specify a username and host combination. What this does is tell you the key that it's trying to install. This text here is just confirming which key that I'm trying to install on the Ada system, and it will install the key by first logging in via SSH. So I need to enter my password now. In this case, we've successfully added our key. So now we can try and SSH in again. And just a quick tip, if you press up on your keyboard, you can go to previous commands that you've typed in. So now when I press enter, you'll notice that I'm logged in straight away and I didn't need to enter a password. Just as a very quick tip, for those who don't have access to the SSH copy ID command, there's a way that you can do this manually. The way that you start is by listing out the public key for your SSH key pair. And the public key is the one that you want to copy across to your remote machine. If I print this out to the terminal, you'll notice we have RSA followed by a long string of random letters and digits, and finally ending in our username and our host name. So what you want to do is select this entire thing and then press Ctrl-Shift-C to copy it to your clipboard. Then what we can do is log into the HPC manually, and in this case you might have to type in your password. And then what we want to do is edit the file in your home directory, followed by .sh/authorized keys. And this is spelt with the American spelling. In this file I'm going to blur out some of these keys, but what you want to do is go to the end of the file and press Ctrl-Shift-V to paste in the full key. If you press Ctrl-X and Y to save, now the key will be stored within this file. And you should be able to log in without using a password. So now we have that set up, I'm going to show you an even easier way to work with the HPC by using VS Code. So the first thing you want to do is open VS Code on a new window. And to connect to a HPC, what we want to do is first make sure we have the remote SSH extension installed. The way that you can install this is by going to the Extensions tab on the left-hand side, and then in the search bar type remote SSH. And this extension is provided by Microsoft. If you click on this, you should see an option to install it unless you have it installed already. Now once you have this extension installed, you should see a green button on the bottom left hand side, which lets you access a remote window. If you press this button, you'll be greeted with a menu, and the one that you want is from Remote SSH, and it's labeled Connect to Host. If you've used this extension before, you should see the previous hosts that you've connected to. Otherwise, you'll just see the Add New SSH Host button, which is the one that we want to select in this case. So here you just type in the regular SSH command that you would use for a normal connection. In this case, it's just SSH, followed by your username, followed by the host name of the computer that you're trying to connect to. Once you've typed this in, simply press enter. You'll also be asked for a file in which to save this information. In this case, I'll just save it in the standard .sh/config file. Once you've added the host, you'll see a pop-up in the bottom right-hand side that asks you to either open the configuration or connect. In this case, we just want to connect to this machine. You'll see a new window open up, and you'll see some details on the bottom right-hand side. If you're connecting to a machine with two-factor authentication, you want to click the hyperlink for the details button, which opens up an output terminal in which you can type in the two-factor authentication code that you need to log into that machine. So once we've connected this machine, you'll see the green icon has expanded to show the host name of the machine that we've connected to. Additionally, if we go to the top menu bar and go to Terminal, New Terminal, you'll see that we've been dropped into a terminal inside this machine. What's useful about the VS Code environment is that we can spawn multiple terminals without having to log in to each one separately. One of the biggest benefits of using VS Code is it allows you to navigate all of your files in a very easy manner. But if you're connecting to the HPC for the first time, you won't have any files on this system, and we need to be able to transfer your files from your local machine onto the remote computer. So let's say I wanted to transfer my code project from my local machine to the Ada HPC. And I'll show you now what this looks like in VS Code by looking at the code that we wrote in the previous video. Now this folder exists on my local machine, and it contains all of the files that I want to transfer onto the HPC. In order to make this transfer seamless, I've created a Git repository and added all of these files into that repository. And this repository has been synced with a website like GitHub, which stores the repository online and allows this repository to be downloaded or cloned onto multiple machines. Now unfortunately Git itself is quite a big topic and is well beyond the scope of this video. So I've left a link in the description to another video which goes through the topic of Git in more detail. For now, all you need to know is that GitHub stores a copy of your code online which can be accessed by other machines. And we'll take advantage of this when we're trying to clone our code onto the HPC login node. For now, I'll assume that you have your code already created and is accessible via GitHub. If you've done this step, then it's very easy to download code onto the HPC. We can just hop straight back into VS Code in the window where we've connected via Remote SSH. We can then open up the welcome menu and select Clone Git Repository. This will bring up a search bar in which we can search for our repository or just paste the URL in. In this case, I want to download the repository called Week 4. And I'll be greeted with a menu to choose where to put this folder. Once you've chosen a suitable location, just click Select as Repository Destination. So once it's cloned, you'll see an option for would you like to open the cloned repository? In this case, yes, we do want to open this. If you haven't set up Passwordless Login, you might be asked to type in your password again. So once you've opened your folder, you want to click Yes, I trust the authors. Now you'll see all of the files hosted in that Git repository available locally on the HPC cluster. And now this version of VS Code is as if you opened VS Code on the HPC login node itself. And so you'll have your entire coding environment accessible from the HPC. We can open up files and make edits just as you'd normally expect. One thing that you'll notice immediately is that by default your extensions aren't installed on the HPC. So if you want to use any extensions, you'll have to go over to the Extensions tab and then type in the extension that you want to use. And in this case, I've already installed the extensions that I'll need for this video. I wouldn't recommend developing your code from scratch on the HPC, but instead developing it locally and then just syncing the changes across using GitHub. In this case, you can just use the built-in source control tab and this ... menu to do the regular push and pull that you'll need to sync changes. But for now, let's head back into a terminal. So now let's have a look at some commands that you can use to interact with the scheduler. And on this HPC, the scheduler used is the SLURM scheduler, which is very widely used across a range of HPC systems. But it's not the only scheduler that's available, and so you should always check the documentation for your local institution to see which scheduler is being used. The first command we'll use is sinfo, and this gives us some information about the current state of the cluster according to the scheduler. This command dumps a bunch of information into the terminal, and in particular it lists all of the different partitions that are available on this cluster, their associated time limits, how many nodes there are, and the state that those nodes are currently in. So there's quite a bit of information here, so let's break it down. The first thing to look at is a partition, and a partition is just a specific queue that you can submit jobs to. Each partition will have an associated set of nodes, which when available can run your jobs. Each partition will have a maximum time limit for any jobs submitted to that partition. And some partitions will have nodes with additional resources, such as HMemQ, which contains high memory nodes. If we look at the state column, this will give you a clue of how busy the cluster is. But let's just focus in on this output by looking at the state of the default queue. We can rerun the sinfo command by giving the -p argument and specifying the name of the def queue partition. In this case, you can see that the HPC is quite busy. 2 of the nodes are unavailable because they're in the drain state, 46 of the nodes are in mixed usage, and 9 of the nodes are completely allocated to tasks. If we have a look at a different partition, short queue, you'll see that all 6 nodes in this queue are labeled as idle, which means they're available and ready to accept new jobs. The trade-off between these 2 queues is that the short queue will have a shorter time limit, and so you can only run jobs for up to 12 hours, as opposed to the default queue in which you can run jobs up to 7 days. So now we have an idea of how busy the cluster is, let's see what we need to do to be able to run a job. The first thing we have to do is make sure we have access to all the software we need to run the jobs that we want. In this case, let's say we wanted access to Julia. If I just type in Julia, you'll notice that this command isn't found by default. And that's because most applications aren't available on the HPC by default. And there's a very good reason for doing this on a HPC system. And that's because the HPC system is shared between thousands of users. And all of these users will have a wide variety of software requirements. And so what HPC administrators do is make sure that the software is installed in self-contained units, which can be optionally loaded by users. If you want to browse through all of the software that's available on the HPC, you want to use the command module avail, which will give you a huge list of all of the software that's available on the system. If there's a lot of software installed, this command might take a while to run. This list is a big catalog of all of the software that's installed by your cluster's administrator. And sometimes multiple versions of the same software are installed. If you want to browse through this list and you're seeing this more icon in the bottom left hand side, you can just hold down enter to print out the entire list. If you're in the VS Code terminal, once you've printed out this entire output, you can just do Ctrl F to find the piece of software that you're interested in. And so you can find that there's a Julia installation for version 1.10.4. So in order to use this, I'll just select this entire thing and use Ctrl-Shift-C to copy it to my clipboard. I can now load this by using the module load command, and I can just paste in the string that I found from the module avail command. So now this is loaded without errors. If I type in Julia again, you'll see this opens the terminal straight away, and I'm dropped into version 1.10.4. If you want to search for a specific module, you can also use module spider and then type in the name of the program that you want to load. What this does is searches through the catalog to show you the possible versions that you have available, and it even shows you a command that you can use to do a more generic search. If you want to unload any software, you can just type module purge, which will unload all of the user loaded modules. But you will see this message that keeps in the SLURM module, which gives you access to the scheduler. If you want to make sure that the same set of software is loaded every time you open a terminal, you might want to add the module load command into your bash rc file. And this file is just a bash script which is launched every time you open a terminal. You can edit this file either using Nano or using VS Code. I'll show you how to use VS Code here. So the way that you open this is go to File, Open File, and then go into your home directory and type .bashrc. You'll be asked whether you want to open this file, and in this case, yes, we do. So in your bash rc file, I'd recommend just scrolling all the way to the bottom and typing the commands module purge and module load, followed by the modules that you want to use on this system. In this case, I'll use the UNEasy version of Julia, which by default will load Julia 1.10.4. If you save this file and then open up a new terminal, type in Julia -- version, you should see this version automatically load, and so you don't need to keep running this module load command every time. So now we have Julia installed, but we know from the introduction to this video that we're not allowed to run code on the login node itself. Instead, we have to submit a job to the scheduler. So how do we submit a job? The first thing we have to do is write a job script. So I'll go to File, New Text File, and then I'll save the file as myscript.sh. And this will be a bash script which we'll use to describe our job that we want to send to the scheduler. Because this is a bash script, we want to start the file with the hash symbol followed by an exclamation mark and then /bin/bash. The next thing you want to do in this script is define a bunch of directives which will tell the scheduler how much resources we want to use for this specific job. In this case, I'll just paste in a few directives and we'll explain line by line what each of them does. The first line here will specify the partition which we want to submit this job to. In this case, we'll use a short queue because we're not planning on running large jobs, and we saw that this queue was mostly idle when we checked the sinfo command from before. The next directive, --n tasks, specifies the number of processes we want to launch. In this case, to keep things simple, we'll just launch one task. On the next line, we specify the number of CPUs that are needed for a given task. On our next line, we specify that our job will only use 4 GB of memory per node that it's launched on. These three directives are very necessary when you're launching a job because you have to specify the maximum amount of resources that your job will use. In this case, if I specify 4 GB of memory, but my process ends up using much more than that, so 8 GB, 12 GB, etc., then the scheduler will cancel our job because we've exceeded the number of resources that we requested. And so you need to give a realistic upper bound for the amount of memory that your job will require. The same idea applies to the time limit that you set for your job. Choosing the right time limit is very important. You don't want to set the maximum time limit every time because the scheduler will find it hard to fit in your job into the overall schedule, and it might take a long time before your job actually starts running. But if you specify a time that is too short, then your job might get cancelled by the scheduler before it is actually finished. And so you want to specify a time within these two extremes. For anything that we do today, 10 minutes is more than enough time. And finally, on the last line, we specify a file in which to save the console output of any scripts that we run. The reason why we save this into a file is because this job will be run asynchronously on a different node, and so we won't be able to see the output of the terminal in real time. In this case, the output is specified with a pattern, and so each file will begin with myscript_, followed by the job ID, which is assigned when you submit this job to the scheduler. In this case, the job ID is specified by the %J symbol. If you read the documentation for SLURM online, you can find many more symbols which will give different outputs. But for most cases, %j is all you need. And using this way of creating patterns for outputs means that we'll get a new file every time we run our script. In my case, I always label the output files with a .out extension, but the extension doesn't really matter here, and you could label this as .txt as well, and it wouldn't make a difference. But right now we have an empty script, so let's start writing some commands. In all of my job scripts, I tend to start by using the module purge command to unload any modules that I might have loaded when I submit the job script. I do this to make sure that when I load the modules, I'm loading the specific ones that I want for this exact job script. Now this way of doing things is just my personal style, and it's not necessary for your job to run. But you want to make sure that when you run your job, all of the software that you need is available at the point of submission. And I find it's easy to ensure this in the job script itself. So now the software is available from within this bash script. We can use Julia to run some software. In this case, I'll just say Julia --threads1 to specify we're only using one CPU thread. And that's because we only specified one CPU in our bash directive. And then I'll have Julia just execute this command, which prints hello world and the hostname from which that command is being run. So once you're done with your script, just save the file and open up a terminal. So the first thing you want to do is make sure that the script is available in your current directory by typing in ls and verifying your script is there. Once you know the script is there, you can type sbatch followed by the name of your script. When you run this command, you'll be given a job ID, which is a unique identifier for your job. You can check on the status of your job by using the sq command. And we want to specify our username just to make sure that we're only printing out the status of jobs that we submitted and not the status of jobs that other people have submitted. You notice the output from this command is completely empty, and that's because the script has already finished running. So in order to delay the script from finishing so we can look at the output, let's just add in a sleep command to sleep for 30 seconds before printing the output. If we run sbatch again and then run sq, you'll see that this job is currently pending and has not yet been assigned a node. If we keep running this command again and again, we can continue to view the status of our job. In general, running this command again and again manually is not very good, and to repeatedly run this command, I'd recommend using the watch utility that's provided in Linux. This is a very simple command where you just provide the argument -n, which specifies a frequency at which to run the following command. In this case, just 1 second. You notice that just now, this changed from pending to running, and it's been assigned comp001 to run our job. This watch command is very useful to keep up, so you can have a look at the status of your jobs. As VS Code allows you to specify multiple tabs, I usually have another tab open to do my regular terminal commands, and I'll keep this watch tab open just to have a look at the progress of my current jobs. As you can see, we have no jobs running, so let's have a look at our output scripts. But if you go to the Explorer, you'll notice that none of the output scripts have shown up. And that's because by default on these systems, new files won't show up until you refresh the page. So you want to go up to the top to this refresh icon and click it, and you should be able to see your new files. So I ran this script twice, so we have 2 outputs. You'll notice that this ran on comp001. So that's really the basics of how you run a job script. So at this point in the video, you'll have a basic idea of how to work with a HPC system and submit jobs. But I want to take a little bit of time to show you a more advanced technique that you can use to interactively develop your code on the HPC without running code on the login nodes. So on every HPC, I add in a bash script which lets me run an interactive compute job on one of the compute nodes. And I launch this interactive job using the screen utility that's available on most Linux systems. If you don't have this installed on your system, you can ask your system administrator to add it into your cluster. And this utility allows us to run this interactive session in the background so that it will continue running even if we close our terminal. And now to schedule an interactive job, we'll use the srun command instead of the sbatch command. This command takes in a bunch of directives which are very similar to the directives that we found in the bash script earlier. So for example, I specify the partition, the number of nodes that I want to use, the number of processes, CPUs, the amount of memory, and finally the time taken to run the job. In this case, I'll allocate a job for 4 hours. And if you want to copy this technique, you can change the duration to suit your own needs. In order to make this job interactive, we want to specify --pty, and then a program on which to launch. Usually you just want to specify this as bash. So this is a bash script which I save inside of my home directory, but the only command that you would actually need is on line 5. So what I'll do is just open up a terminal and go to run this bash script. But if you're creating this for the first time on your own system, what you have to do is first make it executable. So if you use the chmod command and then +x and then specify the path to the file, in this case cpu alloc.sh, And this will tell the Linux file system to treat the CPU alloc script as an executable, which means we can specify this file in the terminal without any additional arguments and press enter, and it will be run as if it was a program. So when we run this command, the SLURM scheduler will give a job ID and queue the job in the short queue partition. Depending on the number of resources that you ask for, this can take a few seconds to allocate. So now our job has been allocated, will be dropped into a terminal on a given compute node. In this case, we've been allocated comp001 again. And we can confirm this by running hostname. Now, since we're on a compute node, we can open up a Julia REPL and start running compute jobs interactively here. This is very useful if you're trying to debug some issues that only occur when you're on a HPC, as you can run code interactively here and work out what's going wrong and open up the file with the issues and fix the problem. Even if you exit out of the Julia REPL, as long as you stay within the bash terminal, the job will remain allocated. One issue that we have is that if we killed this terminal, our job script will be deallocated and we won't be able to use this allocation again. Instead, you can use a feature of the screen utility to detach from this terminal. If you press Ctrl A followed by D, you will detach from the screen and you will be dropped back into the terminal from when you launched the srun command. If you want to return to the terminal, you can just type screen-r and then the name of the job, and this is the name that's specified by the -s parameter when you invoke screen, which in this case I've set to CPU inter for CPU interactive. If I press enter here, you'll see that I'm immediately dropped back into that same terminal. But using these interactive jobs is also very useful if your cluster administrator doesn't want you to use VS Code to connect to the login nodes. A reason why one of the administrators might not want you to use VS Code is that it uses a lot more resources than a simple SSH connection. If, for example, we're editing a Julia file and we're using the VS Code Julia extension, this will use quite a lot of resources just for the language server, which provides suggestions in the editor. But let's say you still wanted to use VS Code, one thing you can do is allocate a CPU job using the command that we run previously, and then connect to the compute node via the login node, so that we can run the VS Code server directly on the compute node instead of the login node to avoid any of these issues. So let's see how we can do this. So let's say we have this compute node allocated already and we want to connect to it using our local machine via VS Code. The first thing we'll need to do is get the host name of this compute node machine that's been allocated to us and copy it to our clipboard because we'll need it later. Instead of exiting out of this terminal and releasing the allocation, what we can do is run Ctrl A D to detach from this screen session so that it remains active. So now we have this set up, we can exit out of VS Code and open up a new window. So now to connect, we want to use the Open a Remote Window button, which is the green button in the bottom left hand side of the screen. Select Connect to Host, and then add a new SSH host. We'll then type in SSH with our username and with the address of the compute node. But we don't want to press enter yet because we have to specify that we want our connection to go through the login node. The way we do this is with a proxy command, -j, which specifies that we want to jump through the connection to the HPC login node. We can now press enter and specify a file in which to save this configuration. Just for curiosity, let's open up this config and have a look at what that -j command did. All it did was specify a proxy jump, which essentially says that we want to connect to the login node via SSH, and then from that login node, connect to the compute node that we allocated previously. And that's because we can't directly connect to comp001 because it isn't accessible from outside the cluster. And so in order to access it, we have to tunnel through the login node. So now that we have that available, let's go connect to host and select comp001. When we connect to this platform, we have to specify the operating system, which for all nodes on the HPC will be Linux. We'll also be asked to confirm a fingerprint because we haven't connected to this machine before and we just want to select continue. So once that has been set up, you'll notice that we're now connected to the compute node. And because we're on a compute node, we're free to run any tasks that we want inside the terminals and work interactively with our code. We don't have to clone in our files again because we already have access to them through the shared file system. And so we can just select open folder and then specify the folder that we downloaded last time. So once you open your folder in VS Code, you'll be able to install all of the extensions you want and run any code that you wish without having to worry about it interfering with anyone else's work. And with all your development plugins added in, you'll have access to the Julia language server, so you'll be able to have IntelliSense while you write your code. Additionally, you're free to open a Julia REPL so that you can interactively develop your code here. And the advantage of this is that you don't need to submit a job every time you want to test your code. You can just run it straight away since you're already on a compute node. This setup is also incredibly useful if you want to access specialized resources such as a GPU, which you might not have access to on your local machine. And so keep this in mind for the next few videos when we start introducing GPU programming. So now we've spoken about how you can run your compute jobs, but how can you get the results from these compute jobs and transfer them back to your local computer? So let's say that you run some code on the HPC and then you save this code into a results file. So for example, this results.json file. If it's just a small text file, you can obviously just copy and paste the results onto your local machine. But let's say this is a much bigger file. What are the ways in which we can transfer this to our local machine? Well, one option you have is to commit this to your Git repository and then download it there, but that's considered very bad practice for Git, and you want to avoid this, especially if your results files are particularly large, because this can mess up your GitHub repository, and it's a lot of effort to try and fix that mistake once you've made it. Luckily, there are some alternative approaches. The first option is to find your file in the Explorer, right-click, and then select Download, which will let you select a place on your local machine in which to save the file, which you can then open on your local machine. The other option you have involves using the terminal. So let's open up a terminal on our local machine and copy the file over using a command line utility called scp. You want to make sure that this is available locally. Scp works a lot like SSH, but it's specifically for copying files. What we want to do is specify a source for a given file and a target of where to save that file. So I'll quickly make a temporary directory in which to store these results and navigate to this directory. I'll then use the command scp followed by the location of the file that we want to copy. In this case, this file is on a remote machine, and so we also have to specify how to log into that machine. We do that in the same way that we would connect via SSH, specifying a username and then followed by the host name of the machine that we want to connect to. Then we want to specify the path of the file in which we want to copy. We do that using a colon and then printing the path of that file. If we go back into VS Code, we can right-click the file and then click Copy Path. If you're in the terminal, you can also type pwd to find the current path and then add on /results to the end. So once you have the path copied, you can paste it in the terminal with Command-Shift-V, and then you want to specify a location in which to copy this file. In this case, I'll specify a single full stop, which indicates that I want to copy this file into the current directory and use the same name. Now when you press enter, it will connect to this machine using your SSH connection, find the file, and then copy it over locally. If you have more than one file to copy, I would suggest zipping up the file locally using the zip utility, which you can find out how to use on the command line, and then downloading the entire zip folder. If you want a more user-friendly way in which to copy files across and you're using Windows, I'd recommend using the program WinSCP. When you open this program, you'll be asked to connect to a new machine. For the hostname, you want to specify the address that we used for our SSH command, and we can specify our username and password. You could specify a password here, or you can go to the advanced settings and go to authentication, private key file, navigate to your .ssh directory and select your ID_RSA file. It will ask you to convert the format, just press save, press OK, and then click login. And now in our connections, on the left hand side you can see our local directories, and on the right hand side you can see the remote directories. And so you can go into the folder that you want, select all the files that you want, and click download, which will move the file from the right hand side to the left hand side. This method is also useful if you want to transfer some code to the HPC without using GitHub. So you can select your file, click upload, and by default this will choose the folder that you have on the right hand side. If you already have that file there, you can choose to overwrite the file, which in this case is fine because they're both the same file. This method is also quite useful because it lets you select a range of files and perform the operations in bulk. Now that we've learned some basics on how to use the HPC, let's see how we can run an advanced multiprocessing job, which scales to use multiple nodes. And so for this example, I've connected to the login node and downloaded the distributed code that we wrote in the previous video. So now let's write a script which runs the pi_estimated_distributed function on the SLURM cluster. Instead of adding to this script to make it run on the HPC, we'll leave the script alone and create an independent script which will call the functions that are defined here. To save a little bit of time, I've already created this script which will run our distributed code. Whenever you want to use distributed on a HPC cluster, the first thing that you want to do is add all of the processes that you'll need for your computation. The way we do this is by pulling in the distributed library first and a separate external package called SLURM Cluster Manager, and this provides a scheduler specific way of connecting up all of the processes that we add using the addprox command. Notice that we're not specifying the number of processes that we add because the SLURM Manager will automatically look for the number of processes specified to SLURM in the job script. What I also like to do is specify some additional flags to use when launching the new Julia processes, and in particular setting the number of threads to 1 to make sure that we're only using the number of CPUs that we requested in our allocation. The next thing we want to do is include our Distributed.jl script so we have access to all of the functions that we defined there. As I'm going to use this script for a benchmark, I've also included a line here to make sure that this function is precompiled. And finally, this script contains a main function which just runs our Monte Carlo simulation using the number of iterations specified by the command line arguments. And finally, there's some surrounding code which prints out our approximation for pi, along with how long it took to run our Monte Carlo simulation. We're also printing how long the entire script takes to run from start to finish. So now that we have our Julia script, we also need a bash script which specifies our job to the scheduler. And again, I've already created this file in dist.sh, which is very similar to the file that we had earlier, but in this case, I'm specifying more resources. I'm requesting 2 entire nodes and 96 processes per node, which in total specifies almost 200 processes to run. Each of these processes will be given 1 CPU and also 1 GB of RAM per process. The next command just specifies the partition in which I want to run, which again is just the short queue. And again, we're just specifying the maximum time taken for this given job. Finally, we specify the output file, which will be written to every time we use a print line statement. One quick note is that if you specify a directory, you must make sure that that directory exists when you submit the job script. If this output directory doesn't exist and you try to submit the job will fail without telling you why it's failed, which can be quite frustrating to debug, so it's something to remember. The final lines in our bash script will just load the correct version of Julia that I want to use. This line just calls our Julia script, and that's all we have to do for our job script. In order to run this, we use the sbatch command followed by the name of the file, which is our job script, which in this case is dist.sh. We can run this in the terminal and then use the sq command to check on the status of our job, which in this case you can see is running. You can also check the status in the watch tab if you have that open. In this version, we've been allocated 2 nodes to run because we requested this in our job script. Once the job is finished running, we can check for the results by looking in the File Explorer. If you can't find the output file, you might want to click the refresh button to make sure that it shows up. So in our output file, you can see some noise that was created when we ran the module purge command. And this is just the preamble of our script, and so we can ignore the output. The next few lines are from our Julia script, which print the approximation that was calculated, along with the time taken to calculate that estimate, and the time taken for the entire script to run from start to finish. You'll notice that the total script time is much longer than the time taken for our actual calculation, and that's because it takes a number of seconds for all of the processes to initiate the communication with one another. In this version, the code took around 14 seconds to run, but in previous runs, this has been as low as 13.6 seconds. So one calculation that you should do when you're using the HPC is work out how efficiently you're using the resources that you request. In this case, we used 2 nodes and a total of 192 cores. And this took around 13.6 seconds. So let's now compare this figure to how long it would have taken to run on the same hardware, but only using a single core. And I did this off screen, but essentially I took 2 estimates for 2 given values of n, and used the fact that the time taken to execute this function scales linearly to create a function which allows me to estimate the number of seconds it takes to run our Monte Carlo simulation for a given number of iterations, using only a single CPU core. I ran this function on the same input size that we used for our distributed job, and it estimates that it would have taken around 2,100 seconds, which is around 35 minutes. Now if we compare this to the number of seconds that it took to run our distributed job, you can see we've sped up this code by around 155 times, which is an absolute massive improvement, but at the same time this is only an efficiency of around 80%. Since with 192 cores we could have achieved a perfect speedup of 192. But now let's have a look at how we can run our MPI implementation and compare the efficiency to our distributed implementation. So this is the MPI script that we created in the last video. The main changes that I've made is to add some print line statements so that we get the same output as we saw for the distributed example. If you're interested in how to write this MPI code, I'd suggest you watch the previous video. But now let's see how we can get this MPI code running on our cluster. The first thing that we want to do is find a native MPI implementation that's provided by our cluster. In this case, we'll use the module spider command to search for any modules with MPI in the name. In this case, the first match that came back was the Intel MPI library, which has a few versions, but we'll use the 2021 version. So what I'll do is just copy this string so we can use it later. To get out of this more view, I can just press Q. So now that we know which module to load, we can write module load followed by the string that we found, and now we should have access to MPI. We can check this by running MPI exec, specifying a number of processes, and then just running a simple program like hostname. And you can see this works as expected. So now we have the right system binaries loaded, we can go into Julia and tell Julia to use those system binaries. We can launch a REPL with Julia -- project, making sure that we load the right version of Julia first. And then once we're in this REPL, we can add the relevant packages like MPI and MPI preferences. I've already got these added, so I will skip this step. But once those packages are installed, we can bring MPI preferences in, and then type MPI preferences.use system binary and call this function. This will find the correct Intel implementation that we loaded earlier, and then create a file called localpreferences.toml to store these preferences, specifying that we want to use the system binary. Once you've changed the MPI implementation, what you should do is go into the package mode and run precompile. This makes sure that all of the packages get precompiled before you start running your compute jobs, and you want to make sure you do this before you run any batch jobs in Julia which use multiple processors. Because if all of your workers start precompiling the same packages, you'll run into a lot of wasted CPU time. This can take up to a few minutes, and even longer if all the processors are trying to compile the same packages at the same time. And so you want to offset this precompilation cost once before you start running your code. But once everything's precompiled, you can just exit out of the REPL, and we can move on to creating our bash script to run our MPI job. As before, I've already created an MPI script, which is very similar to our distributed script that we used previously. In fact, all of the SBatch directives used here are exactly the same as the ones that we used before, apart from the output file name. The only differences here is we use module load to make sure that the script has access to the right MPI binaries. And finally, we add MPI run in front of our Julia command to specify that this is an MPI job. MPI run should be aware of our scheduler and automatically spawn the number of jobs that we need to run our task. The way that you invoke this will depend on the specific version of MPI you're using and the way that your administrators have set up your cluster. But if you're in any doubt, you should contact your IT team or read their documentation. Let's submit this job script using SBatch followed by the file name. And now we can head into the watch tab so we can monitor the progress of our job. So you can see our job started running and it's been assigned comp 002 and comp 003. So now that our job is finished running, let's find the output file. And again, we'll click refresh and select the most recent file. And so in this example, it took around 30 seconds to run the entire script from start to finish. And our previous implementation only took around 27 seconds. But what's interesting about our MPI results is that the time taken to calculate the final result was actually quite a bit faster than our distributed implementation, and in fact was over 1 second faster. I actually ran this a few times and the best time that I got was 12.4 seconds. And so for our MPI implementation, we achieved a speed up of around 170 times. And so the efficiency for our MPI implementation was around 88%. Whenever you're using the cluster, you need to constantly assess how many resources you're allocating towards a given job, and you want to make sure that you're using those resources efficiently. And the only way you can be sure that these resources are being used efficiently is to run some form of benchmark and to understand how your code scales. In general, you want to perform some of these sanity checks whenever you're running new code and trying to decide how many resources to allocate towards a given job. In this case, we allocated 2 nodes to our job, but we could consider allowing our job to run for longer, but using fewer resources. So let's see what happens if I reduce the number of nodes to 1 and rerun our example. So in this version, the time taken was obviously a lot longer than before, but in this time we were using our resources a little bit more efficiently because we were only using a single node instead of 2 nodes, which reduces some of the communication overheads. And here the efficiency is slightly higher, so you might consider this to be a more efficient use of HPC resources. But this is an extreme example of a very parallelizable algorithm. In most cases, your algorithms won't achieve an efficiency that's even close to this 90%. And so you want to be very careful about allocating more CPUs than your code actually needs to run. So now that we understand the basics of how to run some code on the HPC and some workflow tips of interacting with the cluster, let's take some time to wrap up and discuss some additional tips and tricks that you can use to get the most out of using a HPC. So I'm going to start by summarizing the tricks that we learned during this video. The thing that I always recommend when people are starting to use a HPC system is to learn how to use Git, because you'll have a really easy time working on the HPC and transferring your code files between your local machine and the HPC. And this way you're also able to efficiently work on both the HPC and your local machine at the same time without those 2 pieces of code interfering with one another. And eventually you can use Git to sync your changes between each machine. Additionally, I'd also highly recommend the VS Code Remote SSH extension. This allows you to be very productive on the HPC straight away without running into the steep learning curve that you might experience if you are not too familiar with how to use Linux or how to use a terminal. It also allows you to edit files directly on the HPC, which can be very useful if you just need to tweak some of the parameters for a simulation that you're trying to run. The next tip is very generic and doesn't just go for a cluster, but software in general, and that's just to read the documentation that's provided. Most of the questions that you might ask or the issues that you run into can likely be avoided if you have read through the documentation. The documentation provided for accessing a cluster is usually pretty comprehensive and will also give advice specific to the cluster that you're trying to use, and so this is really an invaluable resource. The next tip is to use the interactive jobs, and you can use this for exploratory analysis or to try and debug some errors that you're experiencing in your usual job scripts. If you use the srun command in combination with the screen utility, you can very efficiently allocate some resources on a compute node, and then use the VS Code remote extension to SSH into that compute node and develop your code there without having to worry about possibly being banned from your cluster for running your code on the login node. Next of all, something important to remember is that you have to load your software using the module command. A lot of software is already provided on these HPC systems, but if you run into a package that you'd like to use that requires some system administrator privileges to install, you should ask your local IT team to install this for you. And in my experience, they're very helpful, and they'll usually do this for you within a number of days. There is some software that you can install yourself if you can download the binaries and put them directly inside your home directory. So for example, you can install Julia yourself if you want access to the latest version without having to bother your IT team. So these are all the workflow tips that we covered in this video, but I have some other tips that you should think about if you're planning to use the cluster extensively. One thing that your code can always benefit from is more testing. And for some examples, this can be as simple as testing your code on your local machine first before trying to run it on a cluster. And that's because you can often get feedback a lot faster by running code directly on your own machine rather than waiting for the scheduler to allocate your job to a given node. If you have a bit more time, I'd also recommend investing in writing some unit tests for your code. Unit tests are self-contained pieces of code that will automatically test the other code that you've written. Unit testing is really essential on larger software projects to ensure that your code works the way that you expect it to. And they can also help save a lot of time that you would have spent debugging errors that could have been caught by unit tests. Next tip is to make the code that you write platform independent. So if you're developing your code on macOS or on Windows, you want to make sure that the code you're writing can be run on a different operating system. And in particular, you want to make sure that your code is able to run on Linux, because practically every HPC system that is in use uses Linux as the operating system. Not only do you want to make your code platform independent, but you also want to reduce the amount of dependencies so that it's portable, and you can run it on your local machine or you can run it on a cluster without having to do too much setup. Next of all, when you're running your scripts, I'd encourage you to separate data collection from plotting code, because you want to make sure that you can tweak your plots without having to rerun your simulation from scratch. As you probably gathered if you've watched the rest of this course, I'm a big fan of running benchmarks to estimate how long your code will take to run. When you're developing code that takes a long time to get some results, you should take some time to understand how your code scales with different inputs. This step is also pretty useful because if you estimate that your code will take many weeks to run, you might want to take some time to optimize your code first so that it runs in a more suitable time frame. So for example, if you expect your code will take 1 month to run and you spend 2 weeks optimizing your code and it now runs in a week, you've saved yourself a week of time. If you don't know how long your job will run for, you can't accurately give a time to the scheduler for how long your job should take to run. And this means that when you're running your job, if that job exceeds the time frame allocated to it, then the scheduler will cancel that job and you'll lose all of the results. For this reason, I'd recommend writing some code to save some checkpoints throughout the execution of your long-running scripts, and some additional code so that you can load in your job at a given checkpoint and continue execution from that point. Another tip is to take advantage of some tools that will allow you to view the progress of a simulation as it's running. One prime example of this is TensorBoard, which is widely used in the machine learning community. And I don't have too much time to go into a tutorial on how to use this here, but I might release some resources on this at a later time. And the final point that I really want to emphasize is that you should be efficient with the resources that you use on a cluster. Only use as many resources as you need to complete your job, and keep in mind that these clusters are a shared resource that are used by many different researchers. And so you want to make sure that the resources that you allocate for yourself are being used efficiently. And that's where I wanted to end this video. Using a HPC can be quite a daunting task, especially if you're just starting on your research career. But I hope this video has provided all the resources you need to take advantage of your institution's HPC.